today. So welcome to RISE Learning Machine Seminars. RISE is Sweden's research institute with nearly 3,000 people working on a wide array of topics. The computer science department works on applied AI projects for the benefit of society, and we organize the weekly Learning Machines seminars. This meeting will be recorded, and if anyone wants to be removed from this recording, please let us know. Also, make sure to check out the collection of great talks on our YouTube channel. Today, I have the pleasure to introduce Lena Voita, who is a research scientist at Facebook AI Research, or Meta AI. Lena defended her PhD thesis in 2021 at the University of Edinburgh, supervised by Ivan Titov and Rico Sendrich, the latter of whom will be giving a talk here in Learning Machines at April 20th. Right. So Lena was awarded a Facebook PhD fellowship, and she worked as a research scientist at Yandex Research. I just learned that this was during the time when they put the transformer model in production back in 2017. Lena's work is focused around understanding what and how neural models learn. And today's topic is a journey on interpretability methods in NLP, inside, out, and back. So please, Lena, the floor is yours.
Thank you for such a nice introduction. I'm very happy to be here. Just a small correction, my defense is scheduled later this year. It's not 2021.
All right.
Yeah. So we're going to talk about some of our work with Ivan Titov and Rico Sendrich, who are my supervisors. And it's called A Journey on Interpretability Methods in NLP, Inside Out and Back. And this journey kind of represents things I've been working on during my PhD. And we'll have two big topics in it. First is analysis of NLP models, right? And from the analysis perspective, along the journey, we'll see different types of methods for analysis. For example, we start with mechanistic interpretation, where we'll look at model components. Then we'll look at attribution methods, and finally, we'll see some examples of black box analysis of models. But since analysis does not happen in isolation, the other side of this journey will be devoted to neural machine translation, and this is the task we'll be doing analysis for. And from a neural machine translation perspective, what we'll see is will be a bit different. So we're going to switch points of view from analysis to machine translation and back all the time throughout this talk. And so since whatever analysis you do, it has to make sense for the task you're doing it for, let me give you a bit of context for neural machine translation. Now we'll see how this journey looks from machine translation point of view. As you probably know, in the last decade, machine translation came all the way from traditional statistical approaches to end-to-end neural ones. And this transition was rather remarkable. It changed the way we think about the machine translation task, its component, and what it means to translate. In traditional approaches, researchers split translation task into distinct components. And here, the important thing is that here humans decide what it means to translate. And the way they split translation task is defined by what they think has to be solved to solve translation. And usually here the translation task is split into target side language model, which is responsible for fluency. So whatever you generate has to be a valid sentence in the target language, and a translation model, which is responsible for adequacy. So for the connection between source and translation. And the translation model is in turn split into lexicon translation probabilities and word alignment probabilities. And usually there are lots of handcrafted features. And all of these model components and features are trained separately and then put together in a model. And here, all these components and features correspond to competencies researchers think the models should have to be able to translate, right? When we come to NMT, here everything is very different. So here we train a single neural network that just reads lots of parallel data and somehow gets to learn the translation task directly without splitting it into subtasks. At a more high level, the difference between these two mindsets, because these are mindsets, right? How we approach translation task. So in traditional mindset here, humans used to tell models, hey model, take this, that, and this other stuff. And this is how you solve the task. And the model tells, okay, because what else can it do, right? But in NMT here, model tells us, hey, look how good I am. Reading lots of stuff made me understand things. And here we are, confused, surprised, and asking how. And the question of how is the main question of this talk. And I'll try to answer it, keeping in mind how things used to be done in traditional SMT. And from this perspective, the question of how can have different shades. For example, we can ask whether the NMT model components can take the roles mirroring SMT components or features. We can ask how NMT balances being fluent and adequate, because in traditional approaches, these two competencies were modeled with distinct components. And here, NMT somehow gets to learn everything at the same time. And in more detail, we can look at how NMT acquires different competencies during training and how this corresponds to different models in traditional SMT. And so this is point of view from neuro-machine translation, right? And now our journey can be seen in full. So from analysis perspective, we'll see different ways of analyzing models that are quite prominent. So looking at model components, attribution methods, and black box analysis. And from machine translation perspective, we'll look at model components, the trade-off between source and target, and NMT training process. And for most of this, I will have fun examples to show you, and I hope it will be interesting. Okay, let's start with model components, right? So here, the question is, can NMT model components take the roles mirroring SMT components or features? And the answer is, of course they can. Everybody knows that, right? The standard decoder-encoder attention is closely related to word alignments. And this is the picture from the attention paper from Dmitry Bogdanov, right? But luckily, I have more examples to show you. And let's look at context-aware model and the transformer model. So first example is context-aware translation. And first, what is context-aware translation? So standard MT processes source sentence and generates target sentence, right? As shown in the example. So encoder reads the source sentence, for example, it was hungry, and decoder generates output. And this is transformer, at a very high level. But sometimes source sentence is not enough, does not contain enough information to translate it. For example, here we have an ambiguous pronoun it, that, for example, if we are translating to Russian, it can have 4 different correct translations depending on context. And this is not specific to Russian, but it's for any language with gendered nouns, such as Spanish, Italian, etc. So what we do is we add one previous sentence of context and plug it into the model. Formally, we take at the final encoder layer of transformer, we have one attention layer to context. And we got some improvements in quality, but this is not what we're interested in right now. So what we're interested in is the types of information the model learns. So here we designed a model in a way that interaction with context is limited, right? We have only one attention layer. right? So information from context is coming to model only through this layer. And we can look at what happens. And this is one of the examples of attention map from the source sentence to context sentence. So on the x-axis is the context sentence, previous sentence. There was a time I would have lost my heart to a face like yours. And on the y-axis is the source sentence, the one we need to translate. And you no doubt would have broken it. So here the source sentence has an ambiguous pronoun it, right? And if we look at the types of information this pronoun takes from context, we see that it takes information from the noun it refers to, the heart, right? And it's antecedent of this noun. And so in this way, you'll notice that the model learned to resolve anaphora. And I'm showing you just one example, but in the paper, we evaluate accuracy of this attention as a correct resolution system, and we show that the model indeed learned to resolve anaphora. So this is not cherry-picked example. We evaluated, we compared it to NLP correct resolution system, and by the way, on this specific example, NLP resolves anaphora as the face. So you would have broken my face, which is doesn't really make much sense in this context. So let us come to high-level view. So we see that while traditional approaches engineered special purpose features to handle various phenomena, in NLP, in this particular example for this model, we see that model components can learn to take specific roles, for example, like certain features. And sometimes these features correspond to the ones modeled explicitly in SMT, because anaphora used to be one of the features that researchers added specifically, added manually to SMT models. Okay, but that part was simple because here we designed, we knew where to look, right? We designed a model in a way that we knew where to look. But what about standard machine translation system? What about the standard transformer? Because here, the task of understanding the model is much more complicated because the standard transformer, even the base model, has lots of layers and lots of model components in each layer. In this case, attention heads. For example, the standard encoder has 6 layers and 8 attention heads in each layer. In total, 48 attention heads in just in the encoder. So how do we know, how can we understand which of these attention heads are more important? How do we know where to look? And here we take an idea from computer vision. So understanding for NLP, at that point, understanding what contributes to predictions was not yet natural. But in computer vision, there are a lot of methods which propagate prediction to pixels in an image and try to understand which parts of input or image are important for prediction. And so intuitively, we take layer-wise radius propagation. It's one of attribution methods from computer vision. And intuitively, what it does is that it propagates prediction from output to input and identifies parts of image important for prediction. So the prediction of a classifier is formed from input to output in a forward parse, right? And radius propagation propagates prediction recursively from output to input to identify parts of image important for prediction. So what we do is we adapt this method for transformer, but we do it differently from computer vision. And the differences are, there are 2 differences. So when we propagate prediction through transformer, we don't propagate to input and stop earlier at some layer. And this, we do it so that we could evaluate importance of model components and not input elements, right? So because we're interested in model components and not in input tokens, for now, at least. And the second, we evaluate the importance on average over a data set, not for a single prediction. So what we do is we take all the sentences from our development set, and for each of the sentences and for each of the tokens, we evaluate contributions of, for example, attention heads to prediction. And we do it for each sentence in the development set and for each token. And then we ask on average over a data set, on average over all predictions, which components contribute more? And this is how we identify attention heads that are most important for prediction. And interestingly, we noticed that only a few attention heads are important. And if we look at these important attention heads, we will notice that they play interpretable roles. For example, attention to adjacent tokens, previous or next token, syntactic role, or attention to rare tokens. And let me show you some examples. So this is an example of a positional attention head. It's encoders of attention heads. So this from a sentence to tokens of the source sentence look at each other. And this head all the time for every type of input, it puts almost all attention mass to a previous token in a sentence, right? Previous token, some other heads learn to track syntactic relations. And again, I'm showing you one example, right? But we also evaluated we evaluated accuracy overhead for syntactic relations, and we do show that attention heads learn to track subject some of the syntactic relations in a sentence. Another fun function is when for most of the tokens, this head puts most of the attention mass to least frequent token in a sentence. Maybe it's we hypothesize that it might be some kind of memorization or overfitting where model tries to stick to some cues, to rare tokens, and to memorize some things. So overall, once again, if you look at this, if you come back to this high-level view of the mindset, we see that in traditional approaches, humans used to give features to model, and in neural for neural machine translation, well, it's still hard for us to fully understand how these models work. As a consolation prize, we get to see that sometimes model components learned to extract features that previously were put into models explicitly in SMT. And in this talk, I'm focusing on the analysis part, but what I did not tell you so far is when we looked at the importance of attention heads, I gave you the intuition for one of the ways to do it on attribution methods. We will look at what contributes to prediction, right? But this is only one view on the importance. Another view is looking at what happens when we try to prune attention heads. If we ask, for example, if you force the model to get rid of some attention heads and we see which heads it chooses to prune. This is another view on the importance, and in the paper we look at both of them, and it turns out that the results are the same, which means that the analysis is sensible. And yes, when doing analysis, you do have to worry about that. You do have to worry about that because with analysis, it's very tricky. And there are a lot of things that can go wrong. There are a lot of things that can be interpreted in the wrong way. So the more methods and the more viewpoints you have on the problem, the better. So it's usually good if you have like different points of view, and it turns out that the results are the same. So this is what we do here. And generally, why and how this analysis is important. Well, if we know that only a few model components are important, we can come up with simpler models where some model components are fixed. And there are lots of works trying to do this. And my favorite is the paper from a group from Helsinki. So what they did is that they fixed from the beginning of training, they fixed some heads to be positional, because if you know that there are attention heads that are positional and that they are important for translation, they fixed them from the beginning of training and trained all the remaining heads. And for low resource languages, it gave quite a lot of improvement. And another way it could be useful is that if we know that important model components play interpretable roles, we can build better models by regularization or supervision for entire components. And here there are also quite a lot of work doing that. Okay, so this was an example of things you can do with mechanistic interpretation, and here we looked at NMT model components, and for different models and settings, we saw that sometimes they can play interpretable roles, which can give us a feeling or intuition of how these models work. Let's come to something. If there are questions, you can ask them maybe just now for this part. Are there any questions?
We have a question in the chat, Lena. Let me see if I can read it. From Jesper. Is there a relation between fixed components and sparse transformers who use fixed attention masks?
Yeah, that's exactly it. So that's exactly, these are the same thing, yeah. And the addition is that we know that once we train a model and the model is good, that important model components play some roles. If these roles are as simple as positional heads, we can fix them from the beginning. So we fix attention to some position and train the rest. And this is exactly it. Yeah. Okay, so for now we looked at model components, and now we come to the next point of our journey, where we'll look at more global things, at how information flows across model. And from the machine translation perspective, we'll look at the trade-off between source and target. And what is this trade-off? So in machine translation, usually when we talk about quality, we look at two things, fluency and adequacy. So fluency is agreement on the target side, meaning that whatever a translation model generates has to be a reasonable sentence in the target language. It has to be something that can be said in the target language, right? And second, adequacy is the connection to the source. So the translation has to preserve information from the source. And in traditional SMT, as I mentioned, these two competencies were modeled with distinct models. And in NMT, this happens within a single neural network. And so if we look at the prediction of a network, we'll see that it is based on two very different types of context. So every prediction is based on, first of all, the target prefix, which is previously generated tokens, and the source sentence. But it's not clear what influences predictions, the source or the target. And this is what we'll try to understand. And why is this important? Well, first of all, there's a lot of evidence showing that sometimes models fail to effectively use the source and target, so effectively balance these two types of information. This can be seen, for example, by modeling modifications showing that context gates, which way source and target context help. And this was shown for both RNNs and transformers. And a more interesting example is hallucinations. Because when a model is hallucinating, a model fails to use source, right? It generates content unrelated to the source sentence, like something fluent but unrelated to the source. And there was some anecdotal evidence showing that sometimes we can see that for hallucinations there's deficient decoder encoder attention, pointing to least informative tokens in the sentence. For example, all tokens point to a source end of sentence token, or some informative tokens such as punctuation. But this evidence was rather anecdotal, and as we show in, for example, our latest EACL paper on hallucinations, we show that attention is not really informative for detecting hallucinations. And so coming back to this trade-off between source and target, if we develop the method to understand to what extent a model relies on the source, it could be useful to evaluate techniques for which which force model to rely more on input, for example, different kinds of regularizations, additional loss terms, and I will show you some examples of that in this talk. And to evaluate models for other tasks where reliance on source is important, for example, data to text generation, image captioning, etc. Okay, so now I hope you're motivated enough. So let's come to the details. So we want to understand what influences predictions, the source of the target. And what's important, we want not an abstract quantity, but relative contribution. So we want to understand which part of all the things that contribute to a certain prediction, which part belongs to the source. For example, to what extent, what is the proportion of the source influence on the prediction. And so what's going to happen, I'll give you high-level intuition for the methods, and then we'll look at some experiments. Some of them will be related to hallucinations. So here, the method we use is, again, we take intuition from computer vision, and we adopt, again, Lever's resonance propagation for transformer. And I'm not going to go into details of that, but since the method was originally developed for computer vision, the operations, the propagation operations were defined only for specific layers, such as convolutional and ReLU activations. But for transformer, we had to do a bit of math to adapt it for softmax operations to propagate the transformer and the layer norms and all of that. But that's in the paper, intuition is still the same. Intuition is that we somehow we propagate prediction recursively from output to input to identify parts that are important for prediction. And for images, again, we see this cat face heat map showing that cat is important for the classifier. For NMT, intuition is similar. So we take a prediction, we propagate it back, and we end up with the token contributions. And because of the specific method we use, the sum of all the contributions is constant across the layers. So when we end up propagating, the total contribution of all tokens will be equal to the prediction we propagate, right? So this is so-called conservation principle. So the total contribution is always constant here. And this is why we can talk about relative contributions. This is why we can say that, okay, the proportion of source influence is as follows, right? And what we expect to see when looking at how contributions change during generation is that, of course, for the first token, the prediction is based on the source because we don't have the prefix yet. But as we continue generation, the trade-off between source and target, shown here on the bottom, it can change depending on the token we generate, depending on position, depending on various things. Because, for example, for some tokens, to generate some tokens, you can rely more on the source information, and for some tokens, more on the prefix. And this is what we're about to see. Okay, and the things we look at, again, so we evaluate contributions separately for each target position. So during model generation, for each position, we evaluate contributions. And we look at the total contribution of source and the entropy, because I don't have much time today. I will show you only the total contribution, but in the paper we'll have more stuff. And here we, again, evaluate this on average over a dataset, because we want to understand general patterns of model behavior, right? So what we do is we take a bunch of sentences. For each target position, we evaluate, for example, the total contribution of source at each position, and then we take average. And then we say, okay, on average over a data set, so generally models behave like this. So this is roughly what we do. And first, let's look at one pattern. So this is the total source contribution depending on target token position. So on the x-axis is target token position. So generation progresses from left to right, right? And we start from position 2 because for the first position, source contribution is always 1. and on the y-axis is the source contribution. So what we see is that as generation progresses, the source influence slightly decreases. So we start quite high and then it slowly, gradually decreases, which is expected because the further along you are during generation, on the one hand, there's less ambiguity in which source tokens to use because you already generated something and you already know that, okay, like this part of the source already used, and there's less ambiguity in which source tokens to choose. And on the other hand, the longer the prefix you already generated, the more effort is needed to stay fluent, right? To account, when you continue generation, you have to take into account what you generated before. That's why we see this trade-off shifts towards the prefix, because the model it starts to rely less on the source and more on the prefix. And what's interesting is that for the final end of sentence token and for the final punctuation mark, source influence is much less than for any of the other tokens in a sentence. It means that the decision to complete generation process, so the moment when the model decides, okay, I'm done translating, end of sentence, this decision is made based more on the prefix than on the source, which I think is kind of interesting. Okay, but this was for one model. And now we are going to compare, now we're coming to the fun part where we're going to compare different settings and different models. And we are going to see how this contributions, how contributions differ depending on what we do with the model. And again, I'm going to show you just a couple of examples. In the paper, we have a lot more. This is just to give you an idea of the things we can do with the method. First, we'll look at different, so what happens when conditioning on different types of prefixes. So far, the first figure I showed you was when the model is conditioned on reference translation, meaning that it's the same way as during training. So this is what we do during model training. And now let's compare to prefixes of random sentences. So what happens if we condition on prefix of a random sentence? The first question to ask would be, why on earth are we doing that? Looks like a very stupid thing to do. So I will explain you in just a moment. So let me just show you what exactly we are doing. So what we do is we take, so we have the source sentence, for example, something that means I saw a hungry cat on a mat yesterday. And then we take a prefix of a random sentence, for example, something like the man in a blue shirt. So this, the source and the prefix make sense separately, but not together, right? So the source sentence is valid, the prefix is valid, but together they don't make much sense. That so far doesn't look like a clever thing to do. But the reason we're doing that is that one of the motivations behind this method was to understand hallucinations better, and the simplest way to simulate this hallucination mode is to rely on random prefixes, because when the model is hallucinating, it's generating basically it's generating random sentences, fluent sentences that are unrelated to the source, and this is the simplest way to simulate this hallucination mode. And before we look at the results, let's think of the things we could expect. So we have two types of information, right? The source and the prefix that do not make sense together. And the model has to, or doesn't have to, ignore one of these parts. And from previous work, we know that on the one hand, we know that NLP models can hallucinate, meaning that they can ignore the source, right? From other work, we know that language models can ignore gibberish prefixes and continue generating something reasonable, so they have this self-recovery ability. And in our case, the question is, what will our model do? Because it can support either the source or the prefix, right? Let's see. This is the same figure I showed you before. I just added another graph for contributions when conditioned on random prefixes. And here we see that the model starts hallucinating right away. So the source contribution goes down dramatically, right? And what's interesting is that it happens even for when given one random token as a prefix. So if you get even one token wrong, what happens is that the model thinks, okay, something bad is going on. I'm going to ignore the source and continue the prefix no matter what. So there is no self-recovery ability, and we see that the model starts to hallucinate very easily. Coming further to this hallucination problem, let's look at the connection between hallucination and exposure bias. The previous work showed that compared standard training objective, standard maximum likelihood objective that suffers from exposure bias, and one of the training objectives that does not suffer from exposure bias is minimum risk training. And they noticed that the model without exposure bias suffers from hallucination less. And they hypothesized that this is exposure bias that leads to over-reliance on target history and to hallucinations. This was at ACO 2020, and at that point, so this was just a hypothesis, right? But there was no way to measure this reliance on target history directly. But luckily with our method now, we can measure this explicitly. So let's do it. And what we do, we take several training objectives. So we consider the baseline cross-entropy loss, minimum risk training that does not suffer from exposure bias, and a couple of regularization techniques that are used very often in NMT. This is word dropout used on the source side, when some of the tokens are replaced with random, that also suffers from exposure bias because we're not taking the prefixes. And word dropout on the target side that suffers from exposure bias a bit less, in a sense that some of the prefix tokens are incorrect, and it means that during training the model is exposed to something other than reference translations, right? So let's see what happens with contributions. As expected, we see that even when given random prefix, the model trained with minimum risk training still has much higher contribution of the source. So the model still tries to use the source, and it uses it much more than all the other training objective, and much more than the baseline shown in gray here. And the other training objective that suffers from exposure bias a bit less than the baseline also has a bit higher contributions of the source. It confirms the hypothesis that exposure bias is connected to this over-reliance on target history and on the prefix. And if we reduce exposure bias, this reliance on history and tendency to hallucinate can be avoided.
Lena, a question?
Yeah.
Perhaps you've already said this, but could you shine some light on the y-axis? Sort of what is the magnitude here? What is it?
It's the proportion of source contribution to the generated translation.
So we're still below 0.5 for the MRT.
Yeah. Unfortunately. But this is when feeding random prefixes.
Yes.
If we look at the same for in the paper, we also show results for normal models. For normal models, that's of course much higher, and for hallucinations that are generated by the model, it would be a bit higher, right? Because here we are force feeding random prefixes. That's why it's quite low. But we can see still, even when feeding completely unrelated to the source prefixes, we see that MRT model still tries to rely on source more than other models.
Okay. Thank you.
I have another question on the previous slide. So I'm just thinking very openly now, maybe it's actually equivalent, but I mean, if we can assume that already at the first target token that if the attention is dramatically lower on the source context, if it's possible to use that as a predictor in terms of finding out already when a model is hallucinating or kind of indicating that.
That's a good question, and basically all of my work this year is devoted to this. And first of all, we're not talking about attention, right? Because attention is not indicative of, it's not a good predictor of whether translation is hallucination or not, because for completely healthy translations, we can still see attention maps pointing, like all pointing to the end of sentence. So this is not a good indicator. We're talking about contributions here.
Right.
And
but one thing I was thinking about.
Yes, there is indeed. So if we see, so low contribution can indeed be used as a detector of hallucinations. And if you look at my latest papers, one with the group in Portugal, another with the group at Where, you'll see that it is indeed the case. So your thinking process is completely correct.
So then continuation, maybe you'll get to that eventually, but one thing intuitively that I was immediately thinking of was that if you're able to predict that, would it be possible to actually use that information in the decoding phase as you're doing, let's say, top P sampling, so you can kind of steer the...
Yes, it would read my latest works, two latest works.
All right. Okay. Thank you.
Actually, we can reduce hallucination rate 3 times, at least 3 times. This.
Okay. All right. Great. Thank you.
So we see that there is indeed a connection between exposure bias and the tendency of the model to hallucinate. And finally, we're going to look at the training process. And this is the part, so if you remember in the title, we had this journey on interpretability methods, inside out and back. And so for now we are inside, right? So specifically when looking at training process, we are going to go out and come back. So this is the inside out and back part. Finally, let's look at the NMT training process. And when looking at training, again, there can be different points of view on this. We can look at this process and the same process on the inside, from the inside. And here we'll look at sort of target contributions, and we can look at the outside, right? So what happens with translations? So this is the 2 viewpoints we're going to have. And first, well, since we're still at the contributions part, let's start with the inside view. Here we, on the x-axis, we show the training step, right? And on the y-axis, the total contribution of source to translations. And here we can see how source contribution changes during model training. And here, and also we can look at the entropy of source contributions. And what we can easily see from this graph is that changes are not monotonic, right? We don't know what's going on, but we see that the changes are not monotonic. So first, contributions and the entropy goes down, and we can hypothesize that maybe the model ignores the source and hallucinates, as we saw earlier. Maybe something else is going on. No way to know for sure for now. Then increase, and we can hypothesize that this is when the model learns how to use source. But so far, we are just hypothesizing what's going on, and what's really going on, we're going to look at a bit later. But if changes are not monotonic, it means that during training, the model has some qualitatively different processes. So there are stages with qualitatively different processes. And what's going on at these stages, let's find out. And now we're going to inside out, and we're going to go inside out and look at the same process on the outside of the model. And in our journey, this is where we come from attribution methods and looking at what contributes to prediction to black box analysis, where we assume that we don't know, we're just going to look at the outputs, right? Okay, so And again, since analysis we do has to make sense for the task we're doing it, I'm going to give you again a bit of context for MT, and let us recall that in SMT, models consisted of different components corresponding to competencies the model needs to have, like the competencies researchers thought model needs to have to be able to translate. And the core components used to be target size language model, lexical translation probabilities, and real-world probabilities. And in NMT, everything is learned at the same time. Well, in SMT, these models are trained separately and then combined together. In NMT, somehow it learns all the competencies at the same time. And we're going to look at how NMT acquires these competencies during training. For example, are there stages where it focuses on one or the other competence, or does it learn everything at the same rate? Or for example, does it learn word by word translation first and more complicated patterns later, or is there a different behavior? And this is what we are going to find out. Once again, like, let's look at the same, we're going to look at the same training process from different perspectives. And what we just saw, we looked at model inner workings and how it forms its predictions. And we saw that training is not monotonic, meaning that there are stages with qualitatively different processes. And now we're going to look at model outputs, because this is a black box part of analysis. And we're going to focus on the competencies related to three core SMT components: target size language modeling, lexical translation, and children. And for this, we're going to evaluate language modeling scores, translation quality, and montanicity of alignments. And here I will again have lots of fun examples to show you of the things NMT models do during training. Okay, let's start. So first we'll look at how language modeling scores of translations change during training. See, here again on the x-axis is training step, and on the y-axis is the NLM score of n-gram language model. And we see that most of the change happens in the beginning of training, and the scores go up and peak much higher than scores for references shown in the horizontal dashed line. It might mean that the model generates sentences with very frequent words and n-grams rather than diverse texts. So this is the only way to get this high language model scores. I'm going to show you examples. So wait a bit. And if we look at this early stage of training in more detail and look at different models with different context lengths, for example, from bigram to 5-gram, we'll see that there is a stage where scores for simpler model for bigram are higher than for the more complicated models, for example, 5-gram. It means that the model generates frequent words and bigrams, but larger subsequences are not necessarily fluent. And let us look at the example. So this is the source sentence, 6 months of construction works, this is brutal. And on the left are translations of a machine translation system during generated by an MT system during this different steps of this early stage of training. And to the right is the approximate version in English. So what we see is that first, the model starts by generating the most frequent token, right? And then the most frequent bigram, 3-gram, then starts using some frequent phrases, for example, European Union and the world, which apparently are very frequent in WMT news translation tasks data. And on the later, something reasonable starts to appear. So here we do see that the model kind of ignores the source, right, and starts by blubbering words in the target language. And this is very similar to how little children learn to speak, right? So they hear something and they start blubbering things completely out of context, that's freaking things they hear. And I can confirm that this is the case. For example, last year I spent half a year in Lisbon, and when I moved to Portugal in a couple of weeks, the way Portuguese sounded to me was "Não sou obrigado." So these were the 3 frequent words I constantly heard, and to me, the way Portuguese language works was like "Não sou obrigado." So this is exactly how a machine translation model operates too. So it just tries to repeat what it sees frequently. Next, we'll look at the quality, and we see that here we'll look at the blue score, which is the standard metric for translation quality. Not the best one, but the others look roughly the same. And we also look at token level accuracy for predicting tokens of different frequency ranks. And as expected, we see that rare tokens are learned a bit later than frequent tokens, but still it is not clear what happens at this last half of the training, because usually when training NLP models, you're a bit cautious and you train it for a bit longer until you're absolutely sure that the model converged according to whatever you're looking at. And what's going on in this last part of training is not clear, whether something is going on or not, because not only the blue score is not changing, but also accuracy, even for rare tokens, it's not improving much, right? So what is going on? Luckily, we have one more thing to look at, and it's monotonicity of alignments. Monotonicity of alignments tells how, so if we put 2 sentences, the sentence and the translation, how monotonic would be the translations of words. If we connect the words that are translations of each other, we can evaluate how monotonic these translations are. And what we see, so here's the second half of the training, the one where the blue score is roughly constant, right? And we see that while we don't see changes in the blue score, alignments still become significantly less monotonic. And even after the model converged, if we train it for longer, even after blue converged, we can still see changes in the alignments. It means that neither blue score nor cross entropy or accuracy is not enough to say that the model is converged. And this is not the only, it is not the first time we are seeing that. For example, in our earlier work on context-aware translation, we also noticed that when blue score converges, when training context-aware models with additional context, we see that when blue score converges, discourse phenomena still continue to improve. So the model is still learning some fine-grained things, but we are just not seeing them with the metrics we are using. And now, once again, an example. Here are two models for English German and English Russian. And here are the source sentences and some translations during this late stage of training where the blue score is not changing much. And of course, I don't expect you to understand all their translations. I want you to look at the colors. So the colors correspond to chunks that are aligned to each other. And if we look at the colors, we see that at the beginning of this very stable stage, we see that the translation is almost word by word, right? We can see that all the chunks are perfectly aligned to each other. And here in the Russian example, the model had to skip the word because there was no way to put to translate it word by word in a way that it would stay fluent. So the model, that was a compromise from the model, and it skipped the word. But at the late, when the model converges, like this, we think that it converges later during training, we see that the translations become much less monotonic. For example, here the final green piece, green part, gets reordered to the beginning, and note that these final translations are more natural in target languages. So this final sentences, less monotonic, are more natural for the target language. And okay, so we are almost done. So what we saw is that during training, NMT undergoes the 3 stages: target side language modeling, then learning how to use source and approaching word-by-word translation, and the refinement stage, which is not visible by blue, but visible by increasingly complex reorderings. And finally, so we came inside out, and now is the time to go back, right? And now let's connect the two viewpoints on the same problem. So we looked at the training process on the inside, from the inside and from the outside. And let's connect the two results. We see that the stages perfectly agree. So first, when the source contribution goes down, when the model ignores the source, we see that this is the language modeling stage where the model starts blubbering frequent words and phrases and start just figuring out how target language works. Then when source contribution goes up, a model learns how to translate, and after these two stages, it processes word-by-word translation. And the final stage is in the contributions, we not see a lot of changes, but this is the rodent stage. And also what is interesting with this learning word-by-word translation first and more complicated patterns later is that it's also very similar to how humans do it, right? As a foreign language learners, we usually, when we start speaking foreign language, first what we do is translate from our native language word by word, right? And only when we become fluent, we start using more complicated regular patterns. So yeah, that's it. So again, we saw that one more example where we looked at the same process from different perspectives and saw that the process is the same. And I strongly encourage you to use as many viewpoints you can to make sure that whatever you're seeing is that the way you're interpreting what you're seeing is the right way to interpret it. Yeah, so if we had time for an immediate practical application, I would tell you that knowing that how NMT learns translation during training, and that if we take earlier translations, they are more monotonic, we can immediately improve. I'm not going to go into details here, but we can immediately improve non-regressive translation by 1BLUE, which for translation, for high resource language play and for translation, 1BLUE is quite a lot. So yeah, this is me trying to defend myself, because when you are doing analysis, one of the things you're constantly feeling is that you have to defend yourself and to persuade people that your analysis is useful. So this is it. Analysis is useful. You can use it to improve BLUE score. Yeah, so we are done with our journey for today. And of course, nowadays analysis is much broader than what I showed you. This was just a journey to along the way we saw different ways of looking at things, and I was just trying to give you a flavor of the things you can understand if you do it. But if you're talking about analysis, of course, there are more methods you can use. For example, one of the popular variants is probing for linguistic structure, or you can look at specific phenomena, for example, like how good language models are at very specific things you want them to do. And yeah, that's it. And for the works I mentioned, there are blog posts on my personal page, and that's it.
Thank you, Lena, for this talk. Do you, now you've sort of made these, or you have defined, or you have found these 3 different stages during training. Can you sort of, I know you mentioned that quickly in the end, but can you think of sort of leveraging these in some way? Could you perhaps guide the training to become more efficient or something like that, perhaps through curriculum learning or something like that?
Yes, I can't, but there was work doing that after. Yeah, so one of the papers using our work, they did it. And also, for example, we can make training more efficient. We can try making training more reliable, in the sense that if you see that if we do nothing that early during training, model hallucinates, right? It starts by ignoring the source, which might not be what we want. So what we might want to do is start with a curriculum where we first show very short sentences where the only way to translate them is learn word-by-word translation, right? And we try to see what changes there, and if the model ends up hallucinating less, for example, and yeah, so we can try and do that.
Right. We have a question from Jesper here.
Yeah, so just out of curiosity, in terms of these contributions between the source and target, I was thinking, do the patterns seem similar also for, let's say, decoder-only transformer versus BERT-style transformers?
Great question. Yes. Yes. So for translation, what I showed you is standard encoder decoder transformer, but in the paper we also have results for LSTMs. So two modeling paradigms, right? LSTM and transformer, and two types of training. One is encoder decoder, another is a language modeling style translation, where you concatenate source and the translation, and then you train it as a language model. Right, so this is another way of doing this, and we say that the stages are the same, and the difference is only, for example, for LSTMs, the translations tend to be more monotonic, meaning less natural for target language, right? And the for LM style translation, the first stage with hallucinations and blubbering is a bit longer than for the standard encoder decoder model, but yeah, that's a great question.
Okay, thank you. So just a continuation on the same topic, then I'm not sure if you're aware of at least some of the earlier work in terms of unsupervised NMTs. So I was just curious if you're aware of it, and if kind of this same contribution pattern again, if it occurs in these unsupervised variations where you can maybe have a slightly stricter separation between the encoder and decoder.
To my shame, I must admit, I'm familiar with unsupervised MT very vaguely, but I do know that with unsupervised models, there is a problem of that models hallucinate a lot more, and they have troubles with relying on the source. And I know that one of the papers used our method to like as a sanity check to see even to track how models rely on the source, and to like try different approaches and seeing which of them ends up relying on the source more. So it can be useful in the setting too, but I'm not sure. I haven't seen works trying to look at training stages there. It would be very interesting. Yeah, and also for multilingual models, seeing how it happens with different languages.
Yeah, but doesn't it kind of indicate that, again, it's a very big assumption that, I mean, if you have a stricter separation between the encoder and decoder, if it has an impact on the contribution metric, then I mean maybe there is some relation between that contribution and the exact architecture in terms of how information flows between the encoder and the decoder.
Yeah, you're exactly right. It can be used as a diagnostic, and just when modeling, it can help modeling, right? So to see what's going on, what are the qualitative changes that are happening from one modification or another. Well, that's
a very good talk anyway, so thank you.
Mm-hmm.
Do we have some more questions? Otherwise, thank you very much, Lena, and thank you everyone for attending this seminar.
Thank you.
Next week, we will have a talk by Vincent Solnocki, who is a PhD candidate at Chalmers University of Technology. This will actually be the first hybrid seminar in this series since the pandemic. So we're trying out actually meeting in real life in our office in Gothenburg, Lindholmspiren 7A. He'll speak about the interpretability of regularization for neural networks through model gradient similarity. So this is February 2nd. And then we'll have a discussion session the 9th of February, speaking about large language models and also, of course, ChatGPT. So with this said, thank you very much for today and welcome back.